In chapter 6, we're looking at exponential functions. We're going to talk about logarithms. I'll get to that later. Inverse functions. We're looking at kind of extending our idea of polynomials into what are called exponential functions and how to work with those. We're going to start by looking at an example, kind of a concrete example. Actually, take that back. Before we look at the concrete example, let's look at what an exponential function looks like. And then we'll do a concrete example, actually quite a few, and see where it shows up, this idea of an exponential function. So here's the definition. Here's what it looks like. I'm going to give you some examples here. I'm going to write down a few examples of what this looks like with numbers. The key important thing with this equation here, this function, is that the x, the variable, is in the exponent. So here are some examples. So our function could be 2 to the x power. A and b are some real non-zero number, because 0 to the x wouldn't do us any good. A and b is a positive real number other than 1. It could be that we have a fraction. That's okay. It doesn't say it has to be an integer or a whole number. It just has to say that it's a real number. So 2/3 to the x power. And it could be, if we fill in all the blanks here, 7 times 8 to the 3x. One thing to be careful, you can't do 7 times 8 and get 56 and say 56 to the 3x power. The problem with that is you're not following your order of operations. If you follow your order of operations, let's say x was 2, you would do 3 times 2 in the exponent first. That'd be like your grouping, so you'd have really 8 to the 6th power. But you'd have to do your exponent before you multiply these two numbers together. So don't multiply these together first. We have to do the exponent first. And then we can multiply whatever that works out to be times 7. So that's what it looks like. Here's kind of a concrete model of this. If you drop a golf ball, this looks kind of like a golf ball, a green golf ball. Let's say you're starting at, 5 feet. Or let's go with maybe 6 feet. I'm 6 feet tall. We'll do that. So if I drop it from the top of my head, it bounces. And this particular golf ball, once it bounces once, is going to go 2/3 of the way back up. So it doesn't bounce all the way back up, which seems true when you bounce a ball. It doesn't go all the way back to the top. So it's 2/3. So this would be 4 feet. So if it starts at 6, 2/3 of that would be 4 feet. After the next bounce, it's going to be 2/3 of 2/3 of the height. Remember, it's going to be 2/3 of whatever this was. And that's where we're going to see this repeated multiplication, 2/3 of 2/3 of the height. After bounce 3, it'd be 2/3 of 2/3 of 2/3. And we keep multiplying by 2/3. We keep taking 2/3 of the last height of the original height. So that to the x power tells us basically how many bounces there are, but it tells us how many times we're multiplying 2/3. 2/3 and 2/3 and 2/3 and 2/3 over and over again will tell us where this ball gets to. Now, this is theoretical. Eventually, the ball will stop bouncing. Physics kind of takes over, and the theoretical perfect world of math doesn't quite work anymore. But if you picked a super big number for x, you would still get a height. It'd be a super duper infinitesimally small height, but technically you'll never get to 0. I don't care how big an x you pick. This will never quite stop bouncing, in theory. And that's what we see with this graph here, is that as we get closer and closer and closer and closer and closer to 0 on the bottom, x keeps on getting bigger and bigger and bigger, but it never quite hits 0. We have our asymptote here, a horizontal asymptote at 0, and it'll never quite get there. And so this function, again, the concrete model doesn't quite jive with the theory once you get to super big, like infinitely big numbers. But that's the idea. That's what we're doing. Another place where this shows up is what's called half-life. Half-life would be like if you take a medicine. Now, I'm not trained in any way in nursing or medicine of any kind. So if I get something wrong here, let me know, and I'll change the way I'm saying it. But if you take a certain type of medicine, any type of medicine, really, sorry, there was a brief interruption there. And I know you probably just saw this equation, but I'll kind of walk it through. So the idea is if you take some medicine, let's say ibuprofen, right away in your system it's strong, but after a certain amount of time, it has less potency. Your body kind of metabolizes it and you have less potency. And then after a certain amount of time again, you have less, it goes less and less and less effect. So after, I'm assuming that since it says take every like 4 to 6 hours, after 5 hours is probably pretty minimal in terms of its potency. And so that's the general idea here. And here's the equation, or the formula for this. Says that if we take the initial amount of the substance, so A sub 0 is how much you're starting with. Take 200 milligrams of ibuprofen, times 2 to the power of negative T over K. Now, this negative power, and I'll reference this in a different unit, this negative power is the same as changing this to a half. And I'll kind of show you what that looks like in a little bit, but that's where this half-life comes in. So this 2 here, we could rewrite it as a half and make this positive, and you get the same result. But I'm going to go with the formula that's in the book. So 2 to the negative T over K. T is the number of days, years, months, whatever they give you. So on a time. And K is the half-life. And they'll tell you what the half-life is. So in this problem here, zinc, I think maybe ZN71 has a half-life of 2.4 minutes. So after 2.4 minutes, there's half of the amount of this ZN71 in your system. So if you take 100 grams at the beginning of this whatever substance, after 2.4 minutes, you would get half of that. You have 50 grams. After another 2.4 minutes, you'd have half of that, 25 grams. After another 2.4 minutes. So keep going down by 2.4, 2.4, 2.4. That's kind of the idea. Every 2.4 minutes goes half, 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 half. So that's the idea here, is that every 2.4 minutes, the potency in the system is half of what it is. So the question is, how many grams would be left after 7.2 minutes had elapsed? If we use the formula, this was that formula. It shows up right there. The initial amount was 100. 2 is 2. Negative T, well, T is time. These do match up, and that's important. If the half-life is 2.4 minutes, we need to be talking about minutes over here. So you may have to do some converting to make sure they're both in the same time unit. We're good to go there. So 2.4 minutes is the half-life, K, and the amount of time that we're asking about is 7.2. So we filled in the formula. You plug that into a calculator, be 12.5 grams. And really, if you think about it in terms of not a formula, 2.4 and another, after 2.4 minutes, you'd have 50 grams. After another 2.4 minutes, that'd be 4.8 minutes, you'd have 25, it'd be half of 50. After another 2.4 minutes, that'd be 7.2, you would have 12.5. And so it does work out in our the way we would think it would. I am going to show, no, I'm not, I take that back. And that would be the answer. So that's using that formula to find the answer, 12.5 grams. Compound interest. So I'm jumping to a very different topic now, money. Compound interest is a formula that we're using. I'm going to give you a chance, pause it, write this down, put all the arrows in. Assuming you have this written down then. Compound interest, the concept, if you're not familiar with compound interest, is that if you put money in the bank, after a certain amount of time, they give you extra money as a thank you for investing in their bank. And we call that interest. Compound interest means that you get interest on your interest. So the more interest you accumulate, the more interest you're going to earn. That's the idea of compound interest. It works the other way too. If you borrow money and you're being charged compound interest, you're being charged interest on the interest of the interest. And so the amount that you owe ends up intensifying exponentially. Here's an example. Suppose you put $1,500 into an account. It's got an annual interest rate of 7%. That's a great interest rate, compounded quarterly. Some of the terms that you're going to see for compounding It could compound once a year, where you get your interest once a year. It could compound once every 6 months. We call that semi-annually. So annually is once a year, semi-annually is twice a year. Quarterly would be 4 times a year, like a quarter, 4 quarters in a dollar. So quarterly means that you get your interest every 3 months, so quarterly. You could also see monthly, so it'd be 12. Weekly, I don't think we're going to see weekly, but it might be 52 weeks in a year, and then daily. I don't think we're going to see daily either. Quarterly, semi-annually are probably the most common. All right, and we want to find out how much money is in this account after 7 years. So we're going to fill in the blanks for this formula. The principal is how much you invested, your original investment, or how much you borrowed. So if you borrow money to buy a car, that's your principal. 1 is 1. R is the rate and interest. With this formula, you have to write your interest as a decimal. 7% interest is going to be 0.07 as a decimal. Compound interest formula requires that you use the rate as a decimal. N is the number of times it was compounded, in this case 4 quarterly. And again is compounded quarterly, 4. T is the time in years. That is important. If they say after 6 months, T would be a half, 0.5. Okay, so filling in that formula, we've got our rate, 0.07, our principal, 1,500, quarterly is 4 and 7 years. If I type that in a calculator, I get this. Now, double check that you are able to use your calculator correctly, that when you type this in your calculator, you actually get this number. That is important. If you can't use your calculator correctly, either use a different calculator or ask how to use that calculator. One thing to be careful of as well, context. We're talking about money. And so when we write down how much money we have, we can't say that we have $2,438 and 119344. We have no type of money that gets this small. The smallest we have is a penny, which is 1/100th of a dollar. And so we want to round to the nearest 100th here. So your answer would be $2,438.12. I'm not concerned about the comma, but I am concerned that you round it correctly. And so make sure you are rounding your answer correctly to the nearest penny for money. Okay, graphing exponential equations. So I'm going to stop here, and I'm going to show in a separate video. We're going to do this in a couple different videos. How graphing looks algebraically, how it looks in the equation, and I'll do a video on how that looks and show some examples. So I'm going to stop here.